Hear me? Yeah.
Sorry, I'll just give me a second to introduce you. So for the next talk, we'll have Chukwudubem from, let's see, from the University of Exeter. Is that right? Yes. So telling us about the quantum subspace expansion approach for simulating dynamical response functions of Kitaev spin liquids.
Perfect. Yeah, thank you. Good morning, everyone. As you said, my name is Chukwudubem Umeano. I'm here with my collaborators at MPL, Loxon and Ivan, and also work with Alexander Kirienko from the University of Exeter, now at University of Sheffield, as well as Francois Jamet, who's now at Alice & Bob. And today we're going to talk about why do we even care about quantum spin liquids, what are their significance, and then we're going to give an overview of the honeycomb Kitaev model, which is a model for quantum spin liquids and a honeycomb lattice. And then we're going to talk about how we prepare ground states variationally for the field-free model, before moving on to how we can actually extend to preparing the ground states for when you actually add symmetry break-in magnetic field terms. And finally, we're going to talk about the quantum subspace expansion model when we actually apply it to simulating dynamics. First, magnetic order. We know that spins, for example, can be aligned ferromagnetically, so all aligned, or anti-ferromagnetically, anti-aligned. But when we have quantum spin liquids, what we have is this frustration. So for example, a very simple example, on a triangle lattice where you have a spin aligned, anti-aligned, and you're wondering what should the third spin be placed in to actually ensure that you have the lowest energy. And of course, you can align it in either way and you'd have the same energy. So what you have is this degeneracy in the ground state, which basically causes very strong fluctuations in the disordered ground states. And the special thing is that this disorder is preserved even at low temperatures. So this is in contrast to things like paramagnets, which actually go to a ferromagnetic or anti-ferromagnetic phase at low temperatures. And so you have very cool properties, very interesting properties in terms of physics. And for example, it can potentially be used to describe high temperature superconductivity. And we know it's also very important now in terms of topological quantum computing as well. So the honeycomb Kitaev model, this is a model for the Kitaev spin liquid and a honeycomb lattice. And what you essentially have is these set of spins, which are connected by bonds in different directions. So you have X, Y, and Z bonds. And then what you have is these hexagons, which form a plaquette. And then you have these bonds between them. And we know that the field-free Kitaev model, so the one I've highlighted in the green, this is essentially a model that actually can be solved, can be simulated classically using Majorana fermions, but this is only in a thermodynamic limit, and we actually want to see, can we prepare it, first of all, in a finite limit on the quantum computer. And so essentially we can analyze the symmetries of the model, and we know that we have these plaquette operators, which are formed by basically multiplying around the plaquettes that you saw, around a particular 6 hexagons, so you get these 6 body operators. And if these define a symmetry of a model, define the presence or absence of vortices. And you can actually take the expectation values of the total vortex operator, and it tells you the total number of vortices within your system. And what we know is we have this vortex number conservation, which means that every plaquette operator actually commutes with our Hamiltonian. And then we also have these loop operators, which comes from the fact that we've actually placed in this model on a periodic boundary conditions, which means we have these loops that go around our torus. And together these form the abelian stabilizer group of our model. And so we can use these symmetries to actually help us with the VQE, as we know that initial state preparation is often very important in this process. So first, what we can do is initialize the system as an eigenstate of our stabilizer group. So we do these projections with our plaquette operators and our loop operators to actually prepare this initial state. And then we can actually then place the system into the correct vortex eigenspace. So we know generally when you go above very small system sizes, the zero vortex sector is where the ground state is. So you can just do these creation and annihilation operators with single qubit rotations to actually place your system into the correct subspace. And once you're in this subspace, you know you don't actually need to leave it, so you can actually use the symmetries and define these generators by essentially having operators that commute with your plaquette operators. And this ensures that you still remain in the right symmetry sector, but you can still actually change the energy to find the ground state. So you essentially have these evolutions defined by these centralizers, and you can have layers in the X, Y, and the Z direction. And basically by having multiple layers of these, you can actually prepare the ground state. And essentially what you see is that as long as you have enough layers, you can see that it actually converges very well to the correct energy almost within numerical precision, as long as you have the correct depth for your ansatz. And this is also good for the infidelity as well. But yes, the pure Kitaev model is interesting, but now if we actually add these symmetry breaking terms, what actually happens now? And we know that basically the ground state degeneracy lifts now. You don't have this vortex symmetry conservation anymore, and the Blanquet operators no longer commute with this full Hamiltonian. So now this VQE process that we described already is no longer too effective. So what we now go to is this method called quantum subspace expansion, and this is something that sort of lies in between variation of quantum eigensolver and QPE in terms of complexity, in terms of the circuit depths, etc. And what you have is this reference state that you can actually choose as your ground state that you've already prepared with VQE, because you know that this reference state needs to have a high overlap with your full ground state, so it's a good choice to choose the non-magnetic field ground state as your reference. And then you basically build up this basis by applying time evolution on your initial reference state. So you choose a particular time step, which can be defined based on your spectral width, kappa, and then you basically apply these time steps with a particular different number of layers, and this basically builds up your basis for your ground state. And you know your ground state wave function can be written in this particular way, and you just need to find now the coefficients that will build up your full ground state. And so then you need to calculate matrix elements. So essentially you need to calculate these overlaps. So you have the Hamiltonian matrix and your overlap matrix, which needs to be calculated with methods such as the Hadamard test or other ways to actually calculate these overlaps. And once you have these matrix elements, which are calculated on the quantum computer, now you can do the rest classically and solve this generalized eigenvalue problem. So you have your H and your S matrix, and you can solve this problem classically, and you'll find your coefficients as well as your ground state energy. And then we essentially see this, so we simulate it for 4 and 6 maquettes, which is 8 and 12 qubits, and we see that as long as you have sufficient number of basis states, so n phi is the number of basis states which you define by how many time evolutions you apply, and you see as long as you have enough basis states, you're actually able to converge very well to a good energy, which is good enough to do physics calculations. And also, if you apply trotterization as well, so on the left we just do exact time evolution state vector simulation, but now we apply trotterization, so we actually trotterize the Hamiltonian terms, and we see that even with trotterization errors, it does very well in terms of actually converging to the correct ground state. And now to briefly touch on the Green's function. So we know that we can define the Green's function. We have the greater and the lower Green's function, and we can define it in this particular way. But how do we actually prepare it using this quantum subspace expansion approach? What we do is we have, again, a reference state, which is now built off the ground state we've already prepared, but now we have this annihilation operator applied onto it, and this can be done with some Pauli operators. And once you have this reference state, you now build up the Krylov spaces again, so you have this time evolution again on your reference states, and you can change the number of basis states depending on what you actually need. And again, calculating matrix elements. Now you have 3 different matrix elements, with a third one, which is this sort of transition matrix, which corresponds to the overlaps between your ground state basis and your Green's function basis. And now you can calculate the coefficients. I haven't actually included the equations for the coefficients, but essentially they come from the 3 different matrices that you've actually calculated already. So again, this is now done classically, just matrix multiplication. And then you insert these coefficients into your continued fraction, because you've gotten your basis of the Green's function in the Krylov basis, it allows you to write your Green's function in this sort of continued fraction basis. And as long as you have enough coefficients, you have a very accurate Green's function. And essentially what you see is that it works, especially even with trotterization errors again. And what it shows is that the method is very robust to these trotterization errors. So what I show is the Green's function as well as the density of states and other spectral functions, and you see that you can't even really see the difference between the different lines because it's very, very minute differences. And then we can even calculate more complex things such as dynamical structure factor. So this is you need to calculate a lot of different Green's functions and combine them together, but you can still actually get something that's very close to the Langevin method, exact diagonalization, etc. And that's essentially where I want to conclude. So we've shown that we can actually use VQE when there is absence of a magnetic field, but then we can actually extend it with the quantum subspace expansion approach to calculate the Green's function as well as the ground states when you do have a magnetic field. And this can be extended to different quantities as well. And yeah, that's what I want to conclude.
Thank you very much. Any questions? If not, sorry. Oh yeah, all the way back. Yeah, you can come over here. Perfect.
Thank you for the nice talk. I just had a quick question. Could you also do this for, say, the extended Kitaev-Heisenberg model? Because like in a realistic material, you can have Heisenberg terms, but the terms that lead to like some more unique like magnetic orders. So could you do the same thing?
Yes, that's actually something we discussed a little bit in the paper. But yeah, as long as you have this reference state that is close enough to your extended model, then yes, you can do this.
Okay. Thank you.
Right.
Great. Let's thank the speaker again.